All right, so I wanted to just wrap up this section 3.1 with a little bit of vocabulary, just to make sure we've got it. And so let's suppose we have a problem where we're trying to maximize z equals x plus y, just a really simple problem, such that I'll just make up a set here. How about if we're maximizing it over this region? Okay, so a couple of vocabulary points are that our objective function is the function that we're maximizing or minimizing, and so in this case it would be z equals x plus y, or you could say this is f of x, y, right? Good. And then we have the x and y are decision variables. Okay, and then if you see the abbreviation URS, that means unrestricted in sign. I'll remind you of this as we go along. Okay. Now, points that are inside of our domain are called feasible points. Okay, and algebraically, feasible points satisfy all conditions, right? If you plug in those numbers for x and y, you would get a true statement, for example. Okay, isoprofit line. An isoprofit line means, in this case, for example, suppose I say k is equal to x plus y, where k is some fixed value. Then we see that y is equal to minus x plus k. And so what is this in our graph here? This is a line with slope -1 and intercept k, right? So you can see that for different values of k, like this might be k equals 2, k equals, I didn't label anything, k equals 3, k equals 4, and so on. You can see that any point along this line would have the same profit. And so an isoprofit line is a line for which every point has the same given profit. So isoprofit line. You can also think of it as a, what is that called? Where you have a level curve for z. Or you could think of it as points on which the profit is some given constant. In this case, we used k for the given constant, right? Good. And then, of course, we have the optimal solution, which is the point or points. Point or points that yield the max or min, depending on what you're after. Okay, that's all the vocabulary. Now, a couple of problems in section 3.1 give people a little bit of a problem. So let's take a look at problem number 4. First of all, I'm just giving you a hint in problem number 4. So we have two types of trucks, trucks 1 and 2, and we have two different paint shops, I think. Let's see, trucks 1 and 2, each truck has to go through the paint shop and then the assembly shop. The paint shop, so there's two shops. It's like paint and assembly. Okay, so we're told that if we only have trucks of type 1, we can paint how many trucks? 800 per day. So if we have only trucks of type 2, we can paint 700 per day. Okay, so if we have X1 trucks of type 1 and X2 trucks of type 2, can we formulate a constraint? So this is this is a problem that tends to trip people up a little bit. So let's think about this. If I have X1 trucks of type 1, I could paint 800 per day. So I'm thinking of putting this in percentages as a way of looking at this. So in other words, I'm going to let, so the constraint is going to be the percentage of time, or percentage of trucks 1 plus the percent of trucks 2, trucks of type 2. And so if I sum those together, I'm going to be getting a 1 for 100%. So for example, we could try one. Suppose I've got 400 trucks of type 1. Right, that means that I've got half the day is for truck 1, right? In other words, 400 over 800. So the percentage for truck 1 of type 1 is going to be X1 divided by 800. Right? And then what's the percentage then for type 2? Or for trucks 2? X2 divided by 700. And if I add these two percentages together, I get a 1. Good. So this is a little bit different than what we were doing before, but we end up with something that we can work with. Okay, so this would be the constraint for the percentages. So I think you guys can probably finish off exercise 4. Now let's take a look at exercise 5, number 5. Why don't we allow... Oh, let me say it a different way first. Constraints must be of the type A11 x1 plus A I didn't need 1 just A1 AN xn less than or equal to BN, for example. Why am I including the equality sign? That's the question for number 5. So why not A1 x1 plus AN xn is just less than BN? Well, what would this do? So for example, what if I plot in the plane that I have the constraint x plus y is less than 1, for example? Well, that would correspond to y being equal to minus x. If I look at where the equality would be, it would be minus x plus 1, right? But I don't include the inequality here, right? So I would end up with a dotted line here. And do you remember what we said about that? If this is the set of points that we have for our domain, then the domain is not closed in this case. So we have to have This does not work then for a good domain. Why does the domain need to be closed? For the extreme value theorem to work. For the extreme value theorem to be valid for us, we need our domain to be closed and bounded. Okay? So in this case, our domain would not be closed if we do not put an equal sign there. Okay, so that's why we don't allow a linear program to have a strictly less than or strictly greater than constraint. Good. Okay, so that concludes section 3.1. We'll start in 3.2 in the next section.